Good morning, students. So today we are going to again continue our discussion on uninformed search technique. Okay, and probably in our next session, okay, we would be able to end up with this uninformed search technique. Okay, so yeah, today we are going to see another search technique which also belongs to the uninformed search category. We'll just first of all, quickly recall what exactly we mean by uninformed search. Okay, so we already know that if the search strategy goes ahead and ahead, okay, without any other information on whether it is going on a correct path or not towards the goal state, then that kind of search strategy is basically known as uninformed search. Okay, and it is also known as blind search because just there is an expansion of nodes. Okay, it is not sure whether the expansion of the nodes is into the correct direction or not. Okay, so that kind of strategies basically are known as uninformed search category. Okay, and if we recall, okay, what all uninformed search categories we have seen. So we have seen about breadth first search, we have seen about depth first search. Okay, we also saw about what is known as iterative deepening depth first search. Okay, and yeah, today we are going to understand the another category, okay, of searching, okay, which is also we call it as uninformed search. Okay, so today the discussion will be on something which is known as bidirectional search. Okay, and at the end, once we complete understanding about bidirectional search, okay, whatever search techniques we have seen till now, okay, we are going to do a comparative study in terms of certain parameters. Okay, which actually which actually help us to understand that how these search techniques are going to work given a specific state space. So that will be a small part of comparative study. Okay, because almost by today we would be understanding 4 different kinds of uninformed search techniques, and after that one more will be left. Okay, maybe after we cover that we can again have a discussion on all 5 of them and understand how they work. Fine. So today we are going to deal with a totally different kind of search technique. Okay, again, basically, okay, this is not going to this is not a searching mechanism like a breadth first search or a depth first search. Okay, as I have already told you that breadth first search and depth first search are something, okay, which are going to behave as very core searching techniques. Okay, and no matter any other uninformed search technique that we use, they have to either follow the breadth first mechanism or the depth first mechanism. But why there is an why there are new search techniques, okay, even in the uninformed category? The reason is only that the core breadth first search and depth first search will end up with certain limitations. Okay, talking about a big state space. Okay, or either they consume lot amount of time, or it may be possible either they consume lot amount of memory. Okay, so so to to maybe optimize that. Okay, or maybe to have a more better working of these breadth first search or depth first search, some additional search techniques are there which just gives direction to breadth first search and depth first search, that okay, rather than working it in the way that you were working. Okay, rather than working into the core way that you were working. Okay, put these additional features into your search and then start working. And that's what we saw when we understood what was iterative deepening depth first search. Okay, so ultimately the searching was happening using the depth first search only. But then basically what happened is that we limited the depth. Okay, and by limiting the depth, okay, limiting the depth was a concept of basically breadth first search. Okay, but the searching of every node basically happened with the help of depth first search only. But then depth first search was telling that to start from a root node and go till the end of the depth in just one trace, and then to backtrack every movement. Okay, but rather than iterative deepening depth first search tool, okay, rather than doing that, okay, do the depth first search. Okay, use the same mechanism, but don't follow the same mechanism till the end of the depth. Okay, we'll restrict the depth. Okay, we'll say that as of now depth is this, and we'll keep on increasing the depth, and then you perform the same way that you were performing. Okay, so that's how we say that we put some additional information to normal depth first search. Okay, so what today we are going to do now, today's search technique is going to be comparatively different as compared to breadth first search, depth first search, or IDDFS all. Okay, because these search technique basically works on a different fundamental. But yes, after we understand the fundamental once, then afterwards we are going to perform the searching. It has to be into the depth first search or breadth first search. Okay, and mostly when we are going to make use of bidirectional search, okay, the preference is to make use of breadth first search more. Okay, while understanding the bidirectional search. Fine. So now students, till now, okay, what we have seen is the searching techniques, just explore the state space, and then somewhere, okay, what they see is that whether the goal node is there, and once the goal node is found, they have to stop. Okay, so that concept we haven't seen in any of the algorithm, but yeah, we know that it has to explore the state space, and of course wherever the goal node will be there, it has to stop, and the searching mechanism will not go ahead, and finally the path will be formed, and that path is nothing but what we call it as the start node and the goal node. Okay, so now when we think about a goal state, okay, there can be two scenarios. Okay, one scenario is something like, okay, we are already aware that in the state space the goal node or the goal state resides over here. Okay, so that is one thing. Okay, that while making the state space itself, okay, we know, okay, that at this place, okay, or at this particular state, okay, the goal state is going to be there. Okay, and another situation could be like that goal state, can be found into, let's say, uh, can be derived by using, multiple different directions, or maybe that having these possibility of goal state, okay, maybe at variety of places into the state space. So what we are trying to basically say over here is that one possibility is that we are sure that goal states will be somewhere over here only. And in second possibility, what we try to say is that goal states can be found, okay, at multiple different places into the state space, depending on what direction it has been taken. So now one thing, okay, that we come to know is that it is not necessary that in a big state space there will be only a goal state which will be just residing at a particular place. Okay, so let me give you an example. Let's say if you want to traverse from location A to location B, of course then location B is your, basically, let's say, the goal state. But when you start your traversal from location A, okay, there can be an altogether a different path, okay, which can lead you to location B. There can be another different path, okay, which can help you to move towards the location B. Okay, so over here, basically it is confirmed that, okay, we have to reach location B. And in that case, okay, we understand that the goal state is something which is, let's say, fixed. Okay, on the contradiction to that, okay, let's say you have to maybe win a certain game. Then winning a game, there can be multiple possibilities to win the game. Okay, either if something like this happens, then also you win the game, or something like this happens, then also you win the game, or something like this happens, then also you win the game. So over here, okay, your performance measure was to win the game, and that performance measure or that goal, was being you could be able to achieve it by several different ways. So in that case, all these several different ways are nothing but your goal states. Okay, and yeah, it is possible that goal state, okay, you can achieve by any path, and all these paths, okay, will lead to a goal state which may be differ than the another path, and differ than the goal state which is lying on that path also. So that's what we're trying to tell over here. Okay, so this concept is very, very, very important to understand, that this could be the situations. Now bidirectional search, okay, will be only used if we are aware of our goal state, and if we are sure that our goal state is something which is fixed, and that there will be only certain way only to achieve this goal state. Okay, so that is what the main purpose. Okay, once we'll see it, okay, we can again understand what is the difference. Fine, so let's start with it. Okay, so what we see is that the bidirectional search is a graph search algorithm which finds smallest path from source to the goal vertex. Okay, So the basic purpose of bidirectional search is to find out the smallest path. Okay, but to find out the smallest path, it basically performs two searches at a time. Okay, so why, I told you that it is different. Why it is different? Because if you talk about breadth first search, if you talk about depth first search, if you talk about IDDFS, okay, they were all performing the search mechanisms only towards one path. Okay, they started from source and they moved ahead because they were not sure where is the goal vertex, and they have to, or where is the goal state, and they have to just keep moving ahead and ahead. But in case of bidirectional search, okay, there will be one search which is known as forward search, which will start from the source and it will move towards the, we can say, the goal state. And the second search will be something which is known as the backward search, okay, which will start from goal, okay, and then it will move towards the source vertex. Okay, so one thing is very clear. Okay, if it means that if bidirectional search wants to run, okay, or wants to execute, which means the goal state is something, the information of goal state is something which we are already aware of. Okay, so that is what we want, we have to understand. Okay, and we will also take examples that in which states, okay, or in which situations the goal states will be there, which we would be already aware of. Okay, so bidirectional search, okay, is going to perform in two ways. Okay, it will first run from source towards the goal, and also parallelly, okay, which means this search will also start. Okay, the forward search will also start, and the backward search is also going to start. Okay, and while the forward search and the backward search starts, okay, they probably meet somewhere, because what is happening is the forward from initial node, it is traversing its journey towards the goal node, and from the goal node, the journey is being traversed towards the source node. Okay, so in this scenario, what exactly happens? Okay, and how this scenario is going to be helpful to us? Fine. So that's what about it. Now, bidirectional search replaces single search graph with two smaller subgraphs, one starting from initial vertex, another starting from the goal vertex. The search terminates when two graphs intersect. Now, normally the other searching mechanism were terminating in the case, okay, either the state space is completely explored, or maybe the goal state is found. So in these scenarios, the search were getting terminated, but the bidirectional search is going to terminate when these two subgraphs, which subgraphs, okay, from a big graph or from a big state space, the one searching which has started from the goal node to from the source nodes towards the goal node, and what one search which has started from the goal node towards a source node. Okay, so where these two searching techniques are going to meet, or they are going to intersect, the search is going to terminate over there. Okay, fine. So yeah, we see a visual representation of what we are going to talk about. So now this is a graph given to us. Okay, and yeah, we can see the nodes, we can see their adjacent nodes, or we can see their child nodes or neighbor nodes, whatever we want to call. But yeah, what we see is that the root node or the source node is something 1, and the goal node is 16, which means it is very clear that the goal state is residing at the node which is 16. So that information is known priorly. It is known where is the goal state. That information is known priorly. Again, I'm emphasizing on this word, that whenever we have to make use of bidirectional search, the information regarding the goal state is known. Okay, now provided that goal state is known, okay, what happens is that the journey starts from first of all root. Okay, and it has to simply move ahead and ahead, and it has to start towards the goal, and from goal it has to start its journey towards the source. Now then, in that case, how the searching will start? Okay, so then it has to either make use of breadth first search or depth first search, okay, to move ahead. So as of now, okay, even the forward search as well as even the backward search, they have to basically search only. Okay, which means they have to move ahead and ahead. So now from 1 it has to go towards 16. Okay, so 1 will definitely either use a breadth first search or either use a depth first search and move ahead. So from 1, it might be possible that it jumps to 4, then from 4 it jumps to 8. Okay, whatsoever. Okay, either the breadth first search or depth first search, whatever is performed. But yeah, the probability of breadth first search performance is more over here. So bidirectional search works in its best way, okay, if it is using the breadth first search. Fine. And then now, why not depth first search? Okay, that also we will understand. But okay, so let's say breadth first search is performed, and then it goes to their child nodes. Okay, explore their child nodes. Then it goes to their child nodes. Okay, then explore all of them. Then it goes to their child node. Okay, that's how it happens. Okay, and parallelly at the same time, the same technique has been started already applied to this goal node also. Okay, so from 16, okay, let's say 12, 15 being explored, then afterwards 10 being explored. Okay, then afterwards 9 and 11 being explored. Okay, so now what happens is that the forward search also explored a node which is known as 9, and the backward search also explored a node which is 9. Okay, when this condition happens, okay, when the exploring or maybe the visited node of the forward search and when the visiting or the exploring node of even the backward search, okay, is the same, at that moment the search stops. Okay, and the forward search will have a path, okay, path which is not from source to goal. Okay, but it will have a path which is starting from the source to the intersection node. Okay, so it will if we take this example, then it will have a path which is starting from 1 and somewhere it is ending at 9, and also the backward search will have a path which is starting at 16 and somewhere it is ending up at 9. Okay, so if students, you can visualize, we can, if we intersect these two paths, okay, basically we get a path which is there from 1 to 16. Okay, and while we have got this path, okay, most of the nodes, we have automatically cut short, because let's say when the forward search has started its journey from 1 to 9, it might be possible that it has reached 9 by not exploring certain nodes. Okay, so let's say if we talk an example over here, let's say it might have moved to 9 by using, let's say, 1, then let's say 2, 4, 8 and 9. Okay, which means basically, okay, 3, 6 and 5 were automatically ignored, and let's say the similar case happens over here also. Okay, so from a state space of 16, okay, when bidirectional search was being performed, okay, certain state spaces were automatically not taken. Okay, and we got a path which is starting from what we call it as the source node, and we have reached towards the goal node. Okay, so that's how we found a path, and yes, we can guaranteedly say that yes, this would be the smallest path. Okay, because while finding this path itself, okay, some of the nodes on both the search techniques, okay, were automatically ignored. Okay, and in that case, okay, it will definitely be prevalent that these will be the shortest path which would be possible from the root node towards the goal node. Okay, so that is the main theme line, okay, for this search technique. Okay, it helps us to find the shortest path. Okay, see, it has to keep on searching. Okay, so it is just a strategy which is going to help which is going to help to find the shortest path, but internally, it has to perform search, and when it has to perform search, it has to either make use of breadth first search or depth first search. Okay, so that is definitely going to be there, but it is just a strategy which is telling. Okay, so what is the main theme of bidirectional search? Bidirectional search says, okay, perform two search mechanisms parallelly. That's what bidirectional search wants to say. Second, what it wants to say, while the performing of these two searching mechanisms parallelly, stop at a place where the intersection node is there. Third, what the bidirectional search wants to say is, wherever you have stopped, okay, consider a path, okay, which is starting from the source to that intersection node, and consider a path which is starting from the goal to that intersection node. Okay, join them, and what you will get is the resultant path, which is going to be the smallest path starting from the source node towards the goal node. So that's what is the bidirectional search wants to say. But yes, in the process of doing so, it has to make use of breadth first search, or it has to make use of depth first search. Okay, fine. So now we'll go ahead. Okay, so suppose we want to find if there is a path exists from vertex 1 to 16. Here we can execute two searches. Okay, one from vertex 1 and another from vertex 16. When both forward and backward search meet at vertex 9, we know that we have found a path from node 1 and to 16, and search can be terminated. Now we can clearly see that we have successfully avoided unnecessary exploration. Okay, so that is the main theme and the main purpose of bidirectional search, and the same example, okay, we just discussed right now. Fine. So now we can consider bidirectional search approach when. So when basically, we can say that, yeah, in this situation, or considering this state space, or considering these agent, okay, bidirectional search, which means that whenever we want to consider bidirectional approach, okay, there are certain things which has to be there. If they are there, then only bidirectional search can be performed. Okay, that will not be the case with breadth first search or depth first search or even iterative deepening depth first search. Okay, they can be performed irrespective of anything. Okay, irrespective of whatever the state space is, irrespective of whatever the working of the agent is. Okay, you can perform breadth first search, you can perform depth first search, and even you can perform iterative deepening depth first search. But that will not be the case with bidirectional approach. It clearly says that there are certain considerations, there are certain situations which need to be there. Okay, if we want to perform the bidirectional search. Okay, and what are they then? So very firstly, it says that both initial state and goal states are unique and completely defined. Okay, which means you are definitely trying to say that there is only one goal state. Okay, and there is only one node which is going to represent it. Okay, because if there will be multiple goal states, okay, which means multiple states which represent themselves as goal states, okay, then it is not possible to start bidirectional search. Okay, if there are, let's say, 10 states which represents themselves as goal states, how it can start its searches from 10 different places? And that will be the same with the initial state also. Okay, so initial state and goal states are, of course, now initial states could be unique. Okay, that is completely understandable, but then goal state also has to be unique. The branching factor is same exactly in both the directions, which means it should not be like that when you divide the graph into two portions, okay, one portion of the graph is having a depth, okay, or maybe let's say branching. Okay, let's from one node, let's say 5 branches are getting explored, and on the other end from one node 10 branches are getting explored. Okay, then in that situation also we cannot consider the bidirectional approach. Okay, so we can decide that we can consider the bidirectional search or not only after knowing the state space, only after knowing where is the goal state, only after understanding the state space. Okay, and if the state space and the goal states, okay, are relevant and are following these conditions, then in that case, okay, we can make use of bidirectional search. Okay, so our goal in bidirectional search is to find a path from source to goal. We can use any search algorithm on both the sides. Bidirectional search is more of a strategy than a fixed algorithm. Using BFS on both the sides is most popular option as it guarantees the optimal path. Okay. Now, just a small, we have to discuss over here why we'll not use the depth first search. So now, students, just visualize. Let's say the depth first search started from the source node. Now what is the mechanism of the depth first search? Okay, the depth first search says that it has to go till depth and depth. Okay, so now what happens is, okay, while moving into the depth, okay, when it starts from the root node and when it moves towards the depth, okay, it might end up somewhere over here, or maybe basically it not reaches a point which is an intersection node for both of the search. So what basically happen from goal node, depth first search implements it and it starts ending over here. Okay, and there is no place from there which has to continue, and then basically it backtracks. Okay, then so you can imagine that it will be after a very long time. Okay, or it may also happen that it because the state space over here is very small, but think, okay, even in one subgraph it has moved till the end, and the another subgraph it has moved till the end. Okay, and after they have moved to the end and they realize that there is nothing forward and they have not even reached the intersection node, they have to backtrack again, continue the search. Again, it might be possible that after certain backtracking they are still parallel. Again they'll backtrack, again they'll be parallel, and after so much of backtracking, okay, basically they meet at a point. So yeah, you can use depth first search, but then in that case it will be not be optimal. Okay, because the searching mechanism of depth first search says that it has to go till the end. Okay, and while the process of going till the end, okay, the chances of meeting somewhere in between becomes very, very, very less. Okay, so that's why, okay, whenever we want to make use of bidirectional search, okay, basically if we make use of breadth first search, then it will guarantee you the optimal path. Okay, so now basically where we should use the bidirectional search. Okay, so bidirectional search must be used only when your goal is well defined. So we are taking an example. Example for a Rubik's Cube, your goal is to fill each side with one color, which is your goal, and your current configuration for your cube is your source state. We could use bidirectional search in this scenario. So students, we have to understand over here that when there is an agent who has to solve the Rubik Cube, okay, there is a fixed goal state, okay, which means this state is only known as goal state. Which state? Where all the sides are having similar colors, okay. So that is the only possibility where we can say that the Rubik cube is solved, okay. By none other possibility we can say that Rubik cube is solved or the agent has done his work, etc., etc. So over here you can imagine the goal state is fixed, okay. Or as I told you that you want to go from location A to location B, and if you fix upon that, no, we have to just go to location B only, okay. If that is the case, then yes, we can say that what we can call it at that our source, sorry, the goal node is something, which is defined, okay. So bidirectional search will be used at a place where the goal nodes are going to be fixed, okay. That is the only scenario in which we can call that this state would be a goal state, okay. On contradict to this, but in chess your goal is to checkmate the other player, but a checkmate can happen in thousands of ways, okay. So there will be multiple we can say possibilities, okay, or we can say multiple kind of goal states, okay, which tells, okay, that yes, this situation is now check and mate, okay, or let's say this situation is check and mate. So bidirectional search will not be feasible in those scenarios wherein there will be multiple situations, okay, which can tell you, yeah, these states can resemble themselves to be there, to be the goal states, okay. So that's what we want to say, that whenever we make use of bidirectional search, okay, we should make use in those applications where the goal states are definitely going to be fixed, and that state only represent themselves as a goal state, okay. Now it the this search can also be basically help us to find out the shortest path into the graph, okay. So whenever we want to find out the shortest path, okay, now what is the shortest path, okay, given one vertex and given another vertex, or let's say given one node and another node, if you want to find out the distance between, or let's say a traversal between this node and this node, okay, then yes, bidirectional search will always give us the shortest path, and that's what we have seen, okay. We have selected one source node, we have selected one goal node, we have performed breadth first search into both of the graphs, and what we find out, a path which is the shortest path to reach from source towards the goal. So basically after you identify the path, basically all the states which you need to traverse from initial state to move towards the goal state. So that identification of different states bidirectional search directly gives you, and then you can take particular actions and directly start jumping towards all those states. Fine. The main advantage will be the time for the execution will be reduced to half. So, okay, so if we are just going to make use of breadth first search, okay, the time consumption will be more, but if we are parallelly going to execute both the searching techniques at the same time, okay, then the time the reduction of the time will be half. So rather than considering breadth first search for the whole path, if the goal state is fixed, then bidirectional search can find out the part which is going to be less than breadth first search. Yes, but it is one thing has to be sure over it, that if even only if the goal state is known, if the goal state is not known, then yeah, we have to go to certain um, traditional algorithms, okay, like breadth first search, or maybe depth first search, like that, okay. So only we are going to make use of bidirectional search, and it will be advantageous only and only when we are aware about the goal state, and if that is there, then then the whole process will take a time which is completely reduced to half, okay. So how that is done, that we will also see. So now so this was basically about bidirectional search, okay. Again, if I tell you, okay, what it does, it performs two parallel searches, one search which starts from the source node and it moves towards the goal node, and another search starts from goal node and it moves towards the source node, and somewhere they stop where they find out an intersection node, okay. And in the process of doing this, either they can use breadth first search or they can make use of depth first search, okay. And that's how bidirectional search, okay, will help to find out a path which is the shortest path, which starts from the source node and towards the goal node, and thereby also helps to avoid all the unnecessary states which can be discarded or which cannot be considered into a process from reaching towards this source node to the initial node. Fine. So now when we have understood all these different algorithms like breadth first search, depth first search, okay, then IDDFS, then today we understood about bidirectional search, okay. Uh, uh, what are their properties, okay, or what are their certain factors, or we can say properties with respect to algorithmic perspective, as in that any algorithm. So all these searching techniques are nothing but we can say different kind of search algorithms. So any algorithm, okay, depend on certain properties, or maybe we see the properties and then we decide that whether we want to use this algorithm or not, okay. So we consider a property such as completeness, which means whether the algorithm is complete or not, whether it is definitely going to give us a solution every time, whether it is optimal, does it gives us an optimal solution, okay. What is the time complexity, which means how much time it is going to take, what is the space complexity, how much memory it is going to occupy. So we consider certain factors, okay, we consider certain properties of a searching algorithm, and then we see what is our requirement, okay. If our requirement matches to whatever the properties or factors of the algorithm are, we directly consider that algorithm, or if it is not the case, then we think for the next algorithm. So that's how, okay, given a specific thing, okay. So see, here we have to do searching. Now we just by today, we learned that, yeah, if searching is only want to be done, then you can do searching using breadth first search, using depth first search, using IDDFS, using bidirectional search. Fine, what should I use, okay. What is the requirement of mine, okay. Should I go for breadth first search, should I go for depth first search, okay. So in that case, okay, we have to be very clear what is the working of our agent and what other things, okay, are available to us, okay. What is the processor available to us, okay. What is the memory space available to us, okay. Are we always looking for an optimal solution, or simply we want to search, okay, whether it is optimal or not, okay. That is not our consideration. Whether we always are looking for a searching technique which is definitely going to help us and find a solution only, okay. So that completely depends from from agent to agent. So let's say if you have an agent, okay, a kiosk agent, okay, so there in that case, not necessarily you have to reach towards a goal and the goal should be extremely fast or something like that. No, not necessary. And interaction would be, okay, certain question will be asked to your kiosk, okay. It can take certain time and give you with some different kinds of output, okay. And all these outputs may be relevant, may not be relevant, anything could be there, okay. So basically in that kind of agent, okay, you are not very sure to find an optimal solution only, so you have a flexibility over there to use any searching mechanism, okay, which you want to use. But let's say on the contrary, okay, you are playing you are working with an agent which is very time critical, wherein let's say it has to perform this action in that moment of time only, okay. Then yes, okay, let's say if there is a vacuum cleaner agent and you have configured it for 10 minutes, and in 10 minutes, okay, it has to complete its work. Then it is something goal oriented, time complexity is critical over there, okay. So that's what we want to basically say. And to understand this, okay, what we have to take care is what is the branching factor, what is the shallowest depth for solution, and what is the maximum depth of search tree, okay. So the branching factor and shallowest depth for solution we are considering from a perspective of state space. Maximum depth of the search tree, okay, again we are considering the state space, okay. Everything we are considering of a state space. So if an algorithm wants to run for these state space, okay, it will consider the branching factor, the depth, and the maximum depth, okay. And depending on these scenarios, okay, it will define its properties. Now, every algorithm, okay, to define its property uses something which we call it as big O notation, okay, or what we call it as O notation, okay. And then it defines some of its properties, like what is its time complexity, etc., etc., okay. So the time complexity of these algorithm will also be described using the O notation. So let's just take an example. So if we say breadth first search, okay, the time complexity, okay, it's let's say b raised to d, okay. So what it tries to say is that if breadth first search wants to run, then at max, okay, see, these all are described using the O notation, okay. When we say O notation, which means what, it defines the worst complexity, okay. Worst complexity, which means what, maximum it is going to take this much amount of time. So breadth first search, what is the worst complexity of breadth first search, or what is the maximum time which a breadth first search will take? Now, why we are telling the maximum time? Because it may be possible that the goal state will be found much more ahead. Okay, then it may not be necessary that it may take so much amount of time, but this is the maximum time it will take. Okay, and it will not go beyond that. Okay, so what is the maximum time? It says that it is b, that is the branching factor, raised to d, that is the depth for the solution. Okay, same way it will consider that space, and whether it is optimal, yes, it is definitely optimal. It always helps you to find a path which is, you know, having less nodes. Okay, and completeness, yes, it is also complete. Okay, it will definitely help you to find out a goal state. Okay, now, considering to that, if we consider depth first search, okay, so the time and the space will be b raised to m. Now, what is m? The maximum depth of the search tree. Okay, so that is a difference between, let's say, d and m. Okay, d is shallowest, whereas m is telling you the maximum depth. Okay, which means it goes till the end, and it consumes so much amount of time for whatever branches are there into your search tree, and that much space it occupies. So what we can understand, that maybe the space occupation will be less. Okay, but the optimality and the completeness is less. Because optimal, why? Because it may consider, okay, many branches, and it may not be able to find the solution, and then maybe at the end if it finds the solution. So the optimality is always not guarantee. Okay, and the completeness is also not always guarantee in a considering a very big state space. Okay, if it continues its search till the end and backtracks till the end and backtracks, so searching and backtracking, the whole process happens. For one branch nothing is found, for second branch nothing is found, for third branch nothing is found. So yeah, it may happen that, you know, because of lack of resources, okay, it may not be able to complete itself. But again, that will not be always the case. Okay, this is a generic scenario that we are trying to tell. Now, the next one is iterative deepening depth first search. Okay, so now if we what was the difference between depth first search and iterative deepening depth first search? Was only that, you know, it restricts the depth. Okay, so that, you know, it does not go something into an infinity, and it keeps on searching the wrong paths only. So the time taken and the space taken is very similar to breadth first search. Okay, because the depth has been now restricted, it does not goes to the maximum depth, and because of this parameter, the optimality and the completeness has become yes over here. Okay, and then if we move ahead to bidirectional search with breadth first search. Okay, because we are considering breadth first search to be very optimal with bidirectional search. So then what we see is that the time and the space occupation becomes d by 2, because now the whole depth is being divided by 2, and for those, the searching techniques are going to play their role. Okay, so that is what we say for bidirectional search, that the time taken will be d by 2, the space taken will be d by 2, provided both the searching are working parallelly, sharing the same resources for searching, sharing the same space for searching also. Okay, so that is about basically you know, the bidirectional search. Okay, and the optimality and the completeness is always going to be yes for them. Okay, so yes, that is about, you know, that is about the comparative study. And once we will know another search mechanism, okay, that is the last uninformed search category, we can understand what is the time, space, and optimality and completeness of that, and thereby at the end we can have a whole perspective of different uninformed search techniques, and what are their comparative study. Okay, so okay, so today we understood about, you know, bidirectional search strategy, and also we understood about the comparative study for different uninformed search techniques. Okay, yeah, so that's what for today, students. Thank you all of you. Thank you.